In the last lecture, we looked and saw how we could get an equivalence of the well-ordering principle with the axiom of choice. So the axiom of choice says that for any collection of non-empty sets, we can find a function that picks one element from each of those sets. So there are many, many equivalents. Books are written on equivalence of the axiom of choice. There are literally hundreds in mathematics. So we're going to now today look at a particularly fruitful one called Zorn's lemma. And this is used very often in many branches of mathematics in place of the axiom of choice. So it has a rather different flavor from the axiom of choice or from the well-ordering principle. So we will first of all introduce that lemma, the Zorn's lemma, and then we'll prove its equivalence with AC and so with WP. So I'm talking now to page 57 here in the notes. So preliminary to talking about the lemma, we have a definition here. It's not a formal definition. So any collection G of sets is called a chain if they are a chain or totally ordered under inclusion. I pick any two things in G. Either X is contained in Y or Y is contained in X. So it's called a chain for an obvious reason, right? The whole thing is linearly ordered under set inclusion here. So Zorn's lemma is about chains. Indeed, particularly it's about maximal chains in collections G like this. So Zorn's lemma, which is really a property, right? But so let F be a set of sets so that for every chain of sets within F, right, then the union of the chain here is an element of F. So F may be, well, who knows, all sorts of things, right, here. But if I've got a chain of sets here, G of sets, and they're supposed to be kind of getting bigger as you go through here, then I could take the union of the chain here and the property is the union of the chain. I mean, in general, this might not be in my collection F. We've said nothing about F. But we insist, in fact, that unions of chains are in F. Right? So for any chain, which is a collection of subsets of F, its union is an element of F. So this is the property of F that we're going to use. Then the conclusion is that F contains a maximal chain. So maximal chain is going to be a chain where we can't extend it anymore. Sorry, I said maximal chain. I suppose I really meant maximal element Y. It should be the union of that chain, that maximal chain. So there'll be some set Y here, such that there is nothing in F which is a proper superset of Y. For any Z in F here, if Z is different from Y, then Y is not a proper subset of Z. I mean, another way to say this would be to say that anything that contains Y and is in F is Y. So it's maximal. I can't find anything in an F that contains it. So this Zorn property here of collections F with this chain property, right? This turns out to be equivalent to the axiom of choice and AC. Right? And that's theorem 5.2. Now, this equivalence we've already shown in the previous theorem. So this is the new bit here. So what we're going to do is first show that Zorn's lemma applies AC. We know AC implies WP, and then we're going to show WP implies Zorn's lemma. So we'll have a circuit of implications. Right? So AC, any collection of non-empty sets has a choice function. So let G be a collection of non-empty sets. What we want is a choice function for G. Right? And the trick is simply that we want to use Zorn's lemma, so we have to define the right F. So the trick is defining the right F, right? So that a maximal element is what you want. Well, what we want is a choice function for G. So we want this maximal element to be this choice function for G. So one way to achieve this is to think of F as being the collection of all, well, approximations to choice functions for G, right? Perhaps a little bit of some final choice function. So that's what we do. So we define F to be the set of all partial choice functions. So all choice functions that exist for subsets of G. I mean, we want a choice function to work for all of G. But maybe we don't have one yet. We don't know that. But this will be the definition of F that we'll use in order to ensure that a maximal element is a choice function on all of G. So again, what is F? Little f is in this family of sets, big F, if there are two conditions. The domain of F, right, is contained in G. And the second thing is, for all little x in the domain of F, we have that f of x is in X. So it's being a choice function. So the only reason an F here is not a choice function for all of G is that its domain may be too small. Now notice that there are things in F. This script F here is non-empty, because I can always just take one set from G, pick one element from it, and that ordered pair would be itself then a very simple but trivial choice function for just that single set. So I could say this. Right? Notice F is not empty. I could just say if X is in G and X is not empty, pick any U in this little x, then here XU, this here is a partial choice function with domain just this element X, and therefore this here is going to be an F. So script F is non-empty. Before we apply Zorn's lemma, we need to know that this criterion is fulfilled. For any chain, its union is in F. And you can perhaps see what's coming here. So pick any chain script H contained in F here. So it's a chain of partial choice functions of the kind we want. So this means the domain of the objects in H, right, is also a chain. After all, the objects here in H are sets of ordered pairs, being choice functions. If they're a chain, then they're all consistent with each other, and I can just take their union. But so H, being a chain, has the property, if I pick any two things, for any F and G in H, either F is a subset of G or G is a subset of H, F, as ordered, as sets of ordered pairs. Okay, so now I can just take the union of the things in H. So I'll just set h, little h, to be the union of all the partial functions in big H here. We then have that h is itself a function. We've seen this kind of argument before when we took, in recursion theorem, on, for example, on, we showed that a union of a collection of approximations, which after all are functions, partial functions, itself gave us a function. And what is the union of these partial functions? H is domain. This is the domain of H. This is the union of the domain of the functions f for f in H. So then what else is H other than, again, a partial choice function on a subset of G here? So H has domain, a subset of G. It's a union of these choice functions, so it's a choice function. Therefore, H is in F. And that's exactly what we need to apply ZL. Right? We want that the union of chains is in the collection of sets we're interested in. See, this is just this statement here. I take a chain, ours has become H. The union of H is one of the objects in our collection F. And that's what we've got here. We took our chain H and its union is in the collection F. So now we can cache in and see that ZL gives us a maximal element Y. And that's the thing, that's the gadget we're after, with this maximal element. So by ZL, there is a maximal. And I called it M in F here. And then the claim is it's a choice function on all of G. Not a partial choice function just defined on a proper subset of G, but on all of G. It's a partial choice function because it's in F. The only question is whether domain of F is all of G. Whether the domain of M is G. Since M in F implies that M is a choice function on its domain. Okay, suppose domain of M is not all of G. Suppose the domain of M is not G. So certainly the domain of M is contained in G. Right. So there's something missing. So we suppose X is in G, but it's not in the domain of M. G consists of non-empty sets. So X is non-empty, so we can pick an element. Pick a U in X. We're only choosing one thing here. We're not asserting the existence of a function. If it's non-empty, there's something in it. So I can always pick once. Okay. But then what can I do? I could take M prime and what have I now got? A choice function on a larger domain than that of M. So M prime properly extends M. So M prime is in F, and M prime is a proper extension of M. But M was supposed to be maximal, and nothing extended it. So this is a contradiction. And nothing in F extends it. So this is a contradiction, and there's no such X. So there's no such X, and M is our choice function. M is our desired choice function for G. Here. So this finishes the claim and the proof in this direction. And ZL implies AC. Okay. So there's one direction there. And we now go for the other direction. Instead of going from AC back to ZL, it's somewhat easier if you go from WP back to ZL. Right, so we're going to have to find, right, for given an F of the right sort, maximal elements of chains. That's my statement of Zorn's lemma. Okay, so from the well ordering property, I need to get ZL up here. Right? So this statement. So I'm going to assume I've got an F so that unions of any chains that it's got are members. So again, this picture here. Right. Here's our F. Here's a possible chain G. The union of the elements in G, this Y here, has got to be in F, but also there's a Y in F that's maximal. So with no proper superset in F. So let F be a set so that for every chain G contained in F, we have big union of G here is an element of F. So we want a maximal element of F. So the moment F is just this amorphous collection of things that we don't know much about. But WP says we can well order F. Then we've got a handle on it, right? We've got an ordering on F, so we can start considering things or start considering some kind of construction by stepping through the elements of F given by the well ordering. There's going to be a bottommost member in that well ordering of F, and then a next and a next and a next, and so on. So WP gives us hope for some kind of construction. So by WP, F can be well ordered. So there is some R such that F R is a well order. And by now we are used to the fact that any well order is isomorphic to an ordinal. Here. And let this isomorphism be K. For some alpha. And again, that's all we need WP for, is to get some alpha bijective with F. So we define by recursion, right, a maximal chain So we'll define something that will end up being, we hope, a maximal chain. In F. And we'll just be careful how we build the chain. Basically, we'll look at each of the elements of F in turn, which we can do now. This in turn bit we can do in a nice, well-ordered fashion, because I've got this bijection between alpha and F. And I'll just decide which ones, elements of F, to put into the chain and which ones to leave out. So we start by putting K of 0 here into what's going to be our H. So this is the chain that we're building, H. So I'm just going to describe informally a process that tells us what to do. I mean, now I've got my F here, and I've got everything nicely lined up in terms of an ordering of order type alpha. So I've got my K of 0 here and a K of beta here, K of 1, K of 2, and so on. So I'll start building a chain, and I'll just work my way through these things. So I'll put K of 0 in the chain to start with. Now I'll look at K of 1, the next thing. So if K of 1, and K is a proper extension of K of 0, right? Then I'll put that into the chain. If it's not, then we ignore it and move on to K of 2. Right? We don't put K of 1 into the chain. And so let's suppose K of 1 doesn't extend to K of 0, but maybe K of 2 does. So then we'll put K of 2 in here, because it does extend K of 0. So again, if K of 2 extends K of 0, we put K of 2 into H, and otherwise we ignore it. So we just carry on in this way, right? So in general, so that's how it begins. So we inspect each K of beta right here in turn. If K of beta extends all the previous choices, for any gamma less than beta, so that we already decided to put K of gamma into H, so if this happens, then we'll put K of beta in. But if it doesn't extend all of these previous ones, we leave it out. Right, so maybe there's a lot of things that are in here. We look at all of these K of gammas. Let's call this K of delta, and we're now going to consider K of beta. We just check that it agrees, if you like, with all the ones we've chosen. It properly extends all the ones we've chosen. If so, we put it in. And if not, we forget it. So clearly what we construct is a chain, because all we do is put in proper supersets. this construction, and it only goes on for alpha steps because that's the length of F under the well ordering of R. After alpha steps has created a chain. And the claim is then that, after all, what are we trying to get? Zorn's property, the Zorn property ZL. Right? We want a maximal element. Well, the claim is that our chain here provides that maximal element. I take the union of the chain, and this will give me my maximal Y. So what's the claim here is that Y, this big union of H here, is a maximal element of F. And in a way, it's kind of obvious because of what we've done here. Right? Okay. So the proof here is there's something further I should have said, right? F had the property that for any chain, its union is in F. So here's our H. Union of H is an element of F. So this is just by our assumption on F. So suppose this, okay, we want to show that this is a maximal element here. Suppose I had some Z here, which contains this Y. Contains or equals, right? This Y. Then, because Y here is this big union of H, Z extends every element that's in this chain, right? Extends K of gamma for any gamma such that K of gamma got put into H. But Y is in F, so Y actually is one of these K things. So for some nu less than alpha, Y equals K of nu. Sorry, Z. So should perhaps have been more careful to specify. We're looking for maximal elements of F. So I pick another element of F. And I suppose it contains Y, and we'll show that it equals Y. It contains, well, this is just Y again, right? So it contains all of the K gammas that we put into the chain H. But because it's an element of F, it itself is some K nu. So actually, in the stage nu of the construction, we considered this Z here. So by definition of our recursion, at stage nu, what do? We decided that y was in, sorry, that z was in H here. But that then means z is contained in this big union of H here, but this is y. So if y is a subset of z, z is a subset of y. So there is no z that properly contains y. So y is indeed maximal. And that finishes the claim and the proof in the other direction. And well, ordering principle proves FL. So that is done there. Okay, you might like to think about how to go from AC directly to ZL rather than using AP, WP. It's often the case that choosing the right formulation of something you know is equivalent to AC is perhaps easier to prove a direction in an equivalence. Using choice functions is not always the easiest way to go. Right? Often, as we see here, using WP is an easier way than using choice functions. But it's instructive to try and use AC to imply ZL straight off. Now, I mentioned that there were many equivalents of the axiom of choice. And on the middle of page 58, there's a bunch of these. Right? So let's just look through these. You don't have to remember these by any means. So let's just see what some of these things here say. Okay, these are all equivalent to WP or AC. So the first one, there's the uniformization principle. Right? So it says, suppose I've got a relation, for example, and there's something like in the XY plane. Right? So it's a region in the XY plane. Then it says there's a function which uniformizes the region. So let me give a diagram about how that works or what that looks like. So this is about UP. So here's X, here's Y. So I think of this as X cross Y. Here's a region, R, a relation on X cross Y. So UP says there's a function f from X to Y which uniformizes the region. So the graph of f would look something like this. Yeah. So for any little x over here, there's some y, which is f of x over here. So above any element of X, there may be a whole bunch of things above the fiber, as it were, above X here. But what the function does is pick out one of those. It uniformly finds one of the things in each of these fibers here. And that's why it's called uniformization. So stating that mathematically, we say that there is a function f from X to Y. So the domain of f is the same as the domain of R. So recall that the domain of R is everything that was down here on this line here, coming from something projected down from something in the plane, in the region R there. So this is the collection of x's in X, for which there exists a Y, such that xy is in R. So the domain of f is also all these x's here. This is the first condition to be a uniformizing function. And the second one is to say that just f is contained in R as a set of ordered pairs. So the graph or the picture of the situation is perhaps something like what I've drawn there. So the axiom of choice implies here that for any x and y and for any region, there is a function doing this uniformizing. So we say f uniformizes R here. Various other principles here on this list. The inverse function principle. It says for any onto function h from X to Y, between any sets X and Y, there's a one-to-one function G, which goes back. So that for every y h of g of u is u. I'm not sure that looks a little bit dodgy to me. For any onto function, there's a one-to-one function that goes back. No, that's fine. That's all right. For any onto function, h from X to Y, between sets, because h is onto, there's a way of choosing a sort of inverse to h. There's a g that goes backwards in the other direction. Right? Such that any u in y, h of g of u is u. So you apply g and you apply h, and you get the identity there. Cardinal comparison says, for any two sets, x and y, either there's a one-to-one map of x into y, or the other way around. So we've seen things like that when we were defining cardinals. Hessenberg, for any infinite set, there's a bijection between x and the Cartesian product with itself. And we saw an argument for that, in particular when x was a cardinal. But the same thing holds for general sets. The same argument, Hessenberg, would hold for general sets X. But we need AC for that. We use WP quite heavily in that Hessenberg principle because we put a well order on kappa cross kappa. We need to put a well order on X cross X here to prove that Hessenberg principle. Every vector space has a basis. You might think, oh, we proved that in first year. But actually, if you've got an infinite dimensional vector space, you need an axiom to say that there's a basis. And there are various other principles down there, which we'll leave you to look at. Right? And I do urge you to try some of these exercises here. The equivalences or implications here are reasonably easy, I would say, reasonably straightforward. If there's an implication that's missing, it's perhaps because it's difficult. So for example, in exercise 5.2, you're only asked to go from AC to IFP. That's because going directly from IFP to AC is harder. If you find the forward direction easy, you might like to think about how to do the reverse direction. Likewise, in 5.5, you're only asked to do this in one direction.